So, good morning. Hello. Relax. So, on Monday, there will be our next test. So what I do right now, this is already a test and also final preparation, so to be absolutely sure that we covered everything. What I do today is to summarize what we did with respect to the second part, so integral equations and calculus of variations. There will be no surprise on Monday. So straightforward, clean setup, 3 problems. So Sturm-Liouville, integral equation, and Euler-Lagrange. I will summarize today the methodology and add a few things in order to make it more complete. And after that, I will continue with our summary of the first part of the semester. And then you should be perfectly prepared for the final. The final will just repeat pretty much problems from test 1 and test 2. So, just for complete clarity, that there's absolutely no confusion. So we are here today. So when you do this, what are the dangers, so to say? One danger could be, I did not see it, but it could be about the understanding. So the first writing involving the y on the right-hand side is, of course, the integral equation. And the second writing is the solution. And what we try to do is to find the resolvent kernels, or the gamma. And the procedure to get it is given here. It needs care regarding the design of these Kn. So we need to work with the correct arguments. Otherwise, you will be soon in trouble, because it does not combine anymore, and usually it becomes rather difficult. Then it also needs understanding of the conditions on lambda. So obviously this does not work for all lambda, but the lambda has to be small in a certain sense. And usually there are two conditions. So the usual setup of the problem is that we see a geometric series, and then there's a convergence condition for the series. On top of that, there is a general condition. I showed you this, and I also showed it again when we talked about the last homework. So this involves the maximum of the domain considered, the M, and this condition is stronger, usually. In theory, you can end up with the same condition. So to make it very clear, when you see this problem on Monday, you are supposed to provide the sum for the geometric series. Yeah? So don't give me just the series. And you're supposed to explain under which condition this sum will have a finite value. So this is the condition on lambda. And what you should do is to work with the strongest condition. You should state the condition for the convergence for the geometric series, but what is really required is then the general condition to get a unique solution. Otherwise, it's a pretty straightforward setup, not really bad. I hope you agree. The M condition, you should provide it. That is the strongest condition. That is the condition for a unique solution. Let me double check. Where are you? Last line? Oh, yes. Thank you so much. This was just an illustration of how much care it needs to deal with these things. Thank you. So I provided the correct formulas when I introduced the material, and here I do my best to illustrate again the conditions. I hope everything else is correct. You will see this problem. Any question about it? Very good. Then we did not talk about it, and you will not see it on Monday, and not when it comes to the final. But maybe some of you take the qualifying exam in applied math, and then it depends on the instructor who prepares it of what you will see. And therefore, for completeness, I will introduce it. So again, you will not see this on Monday and not when it comes to the final, but it could be of interest when you take the qualifying exam. This is actually the original procedure that we used in order to deal with Fredholm. The only difference here is that the B is variable. So, and otherwise everything is the same, and we just keep it as is. Actually, one can also consider the B as a variable. Yeah? And here, the only point is that the x agrees with the x in K. Yeah? Otherwise, the way to deal with it is just to keep it and to do exactly the same what we did for the Fredholm case before we summarized our result to switch to the resolvent kernel.
Do you still have the same condition on lambda, where lambda is less than 1
Yeah,
over the max
yeah,
height? Okay.
yeah.
Professor?
Yes.
In the calculus of variations section, under the Euler-Lagrange, the right-hand side of the equality, isn't that supposed to be f sub u?
Yes, I just tried to double check my writing. It's correct. Thank you. So the thing here is not to have more fun with mathematics. The thing here is to understand where the equations come from, which we have to solve. This is a major question. It is just about the question of how can we derive the wave equation, and it is also the question of when we have specific circumstances, what are the most general principles to give us equations. So when you do research, you will quite often run to the question of what is actually the equation that should be considered. And this is here a way to get a very strong justification, which is really important. And in particular, we have here the Hamilton principle in the background, which gives us motivation to look at this. I showed you the approach, and I showed you variations. The thing here is to see the flexible use of philosophy. It is about the epsilon thing, and it could be that the function considered involves more variables than considered here. There will be no trick on Monday. You will see exactly x, u, and u prime. I cannot promise a u. Maybe it will be a v. So, but you should do the same thing. And there will be no u double prime, okay? So then, it is that simple that you should come up with the Euler-Lagrange conditions, equations, in order to find the solution. And obviously, this is not, let's say, the hardest thing on earth, but it needs perfect care. So you will not believe how often I saw stupid mistakes when it comes to these equations. And this is not good because I have little options to give partial credit when all the problem is about 3 lines. Yeah? And if all lines are incorrect, then I'm out of options. Okay? So please be careful with that. And I hope that everybody understands that we have some algebraic functions when we look at fu, bless you, and fu prime. Yeah, so it is like u prime squared plus u equals x. Yeah, and then we differentiate it by x and turn it into a second order ODE. It is not perfect when you say this is good enough for you, but you should solve this ODE, including the boundary conditions. Yeah. The good thing is it is usually not very difficult to double check that we have here the correct equations. Do you have any concern at this point? You will see such a problem. Again, no trick, straightforward setup. So then it comes to Storm-Nearville. So it is good to see the motivation behind doing this. And the motivation is that we have that we usually look at two sorts of heat flow or other substance transport problems. We can have unforced heat flow, or we can have stationary heat flow. And this means that we have in reality, on the one hand, the F equals 0 case, or on the other hand, the lambda equals 0 case. What people do at this point is to try to get the most general solution, which is very reasonable. And this means to look at cases where we have a non-zero lambda and F. And then Fredholm explained us that we can only deal with one of these cases, not both at the same time. We can have a unique solution to the problem if the lambda is not an eigenvalue. And otherwise, we can have non-trivial solutions to the homogeneous problem if we have the case that lambda is an eigenvalue. Again, on Monday there will be no trick. It will follow the problem set up of the last homework, and you will pretty much see a problem where you can work with the AN formula. Okay. So when we talked about the homework, what I saw is a good amount of confusion about the specification of the problem. So the general writing includes P and Q and then an R and an lambda. And on the other hand, you have a very concrete problem. So for this concrete problem, you need to decide about the settings of P, Q, and lambda and R. I showed you this when we talked about the homework, and the setup will be very similar. But you should not try to come up with a, let's say, a very creative solution on Monday morning where you use different settings for P, Q, and lambda and R. So the best is actually to follow the approach that we use to do the homework. Yeah? Yeah?
So, what is the role of R function? I mean, even if we didn't determine it, would it matter?
It matters with respect to the condition to have normalized eigenfunctions. So the R comes in via physics. It could be just the way it is, that there is no F, and the R gives you, let's say, a term that involves the lambda. So in other words, if we talk about the F equals 0 case, then the lambda brings in the eigenvalue usually. So there is physics behind it, and mathematically the way to care about it is to consider it in the normalized eigenfunctions. Yeah. And
do we have a case where both F and lambda are 0? Or
No, this does not make sense. Then usually it breaks down to a very simple ODE. And then there's not much reason to talk about it. Yeah? So, again, when it comes to concluding about the parameters, my advice would be to follow the setup of the homework. Again, I saw quite some confusion. Then you should expect a case where we have let's say, no eigenvalue. So lambda is unequal to the eigenvalue. And the next potential dangers to bring in, let's say, some incorrect things would be to not care too much about the normalization. What what I was surprised about the problems regarding the normalization of these h functions. So usually the case is that r is equal to 1. And then it just needs to make sure, usually we have sine or cosine functions. Then it just needs to involve a square root of 2 in order to make it work usually. Yeah? We did this, I showed you the solution for the homework problem. And this will work again. And then when you see Cn, it is not fine to just give me, let's say, the integral in order to find finally the Cn. When you see concrete functions, and what you will see is some sort of sine or cosine functions, then you are supposed to solve for Cn. And this involves, again, the square root of 2 coming from the eigenfunctions. You can bring with you whatever you want, your tables. So what I do not prefer is iPhone and internet. Otherwise, you are good to use whatever helps at this point. I understand this is about 50 minutes and getting the job done. So you can use such tools. This is not the point. Yeah?
Just to double check.
It comes in usually with hn. So, yeah. So it just depends on the setup of the problem. So it is just the way it is that the hn come in usually with some sort of factor, and then it depends on the cn. Also, in a few cases, I saw little inaccuracy with the definition of L, which is reflected by the correct specification of the force. The L goes with the sign as is, and it produces some sort of negative y double prime. So when the problem is written as y double prime plus 4y equals certain f of x, then you have to keep in mind that the L requires a negative sign. So you have to multiply it with a negative 1 in order to produce the L problem setup. Yeah? Otherwise, I have to take a half point off because it is not fully correct. Sorry for that. Otherwise, how does it look? Again, there will be no major difficulty. It is about knowing how it works, and my understanding is that everybody knows it, and being accurate to make no mistake. So there's one thing that I should add here. So the first writing is one way to switch from the general Sturm-Liouville problem to an integral equation. We talked about this, where we extended the Ly by account for the force. And it is correct that we have here these specifications for G of X and S, including the definitions of V0 and V1. Otherwise, this is only regarding the setup of the problem. And obviously, we still have the Y on the right-hand side, and we need a solution. So the way we addressed it was to simplify this specific writing, which was based on the general Sturm-Liouville problem. And we wrote it like this, that we introduced simply other notation. So we combined G and R to K. And the last term on the right-hand side is just a function of X, and we consider it to be another force. And then it is exactly the problem that we considered before, and it is about solving the problem as an integral equation. So it is just another setup of the problem. I show you this for completeness. Otherwise, what you need on Monday is to know how to solve the green integral equation, and you need to know how to set up and solve the Euler-Lagrange equations. Yeah. So that is pretty much what we did regarding this part of the semester. Does it look good? Yeah.
What are the bounds of the integral and
So they follow, of course, the bounds. So this is just, yeah. So this is just rewriting in order to show the relationship to the problem that we considered before. So it is another sort of motivation of how we come to this problem. Everything is good? Okay. Then let's stop for today. Have a wonderful weekend and see you on Monday. If there's any question on Monday, just talk to me, okay? So if you are not absolutely sure about the wording or something, talk to me. So on Monday we will have a test, and then I don't think that we need the video system.
Okay.
Yeah?
Yeah, that makes sense. I'll let them know.
Okay, thank
You
you.
usually have somebody else on Monday, right?
Yeah.
I'll let them know.
Yeah, it's in my office. So
I'll come.
okay. So you will come this morning, sir?
Yeah, yeah.
Another class from 12 to 1.
No, just right after class, during
Okay.
office hours.
Yeah.
I'll come.
Okay.
That's really awful. Oh, thank you. Tell me your 100. Yes. I don't make really awful fun.